Okay, hello everyone. I'm Tian Kai, and I'm very glad to present our work today. Our topic is about auditing the sensitivity of graphics ranking with visual analytics. So graphics ranking is basically everywhere when we abstract real-world entities into a graph. A very simple example would be the internet. We have countless web pages and hyperlinks, which are treated as graphs when we rank them to retrieve the most popular one in search engine, which is the initial idea of PageRank. Such ranking methods were also applied in many fields. For example, the recommendation system, which is used to provide recommendations based on users' preferences. Those recommendations are also ranked based on graph-like social networks. A classic example of graph-based ranking is PageRank. So imagine this: we have many web pages which may have many hyperlinks point to other ones. Such network can be viewed as a graph structure like this. So PageRank depicts the process that users randomly visit any web pages and may or may not visit another page with the link of that page. This method outputs the converged value for each node, which presents a probability of users would visit that particular page. The higher the probability is, the higher the rank of that web page has. And here we call that probability PR values. Since such ranking methods is based on topological structure, we may wonder, what if we remove the node and its corresponding edges? What would the ranking result be influenced? Here we remove node B, and now the node E is ranked as a top one node as all PR values change. So this phenomenon actually bring us the motivation of our work. We would like to know how such ranking methods are sensitive to the perturbations like that. What the specific ranking changes would certain removed node cause. In real-world applications, changes of ranking positions can have huge impact with respect to the exposure, which requires us to understand the ranking changes methods sensitivities. Let's start with a general definition of sensitivity we're talking about. We refer to the term sensitivity index to denote the degree of ranking method sensitivity to the perturbation of the graph element. But concretely, the sensitivity index of B in previous case is measured by the difference in ranking positions before and after the perturbation. Despite many combinations of measuring the sensitivity index in this work, we focus on removing single node as the perturbation methods and utilized L1 norm as the distance metric, for which we will explain details in the next few slides. Knowing how to measure the sensitivity index, we then propose our visual analytics framework. The overall idea for the framework is to help users to inspectively understand the graph ranking method sensitivity with respect to different perturbations. The framework consists of three major functionalities: identifying the instance level sensitivity, diagnosing the perturbation effects, and the constraint filtering. The sensitivity identification part, we just iteratively remove each node and its corresponding edges to calculate the sensitivity index for each node. And then we integrate the result into a sensitivity index list to show that how the ranking method is sensitive to each node's removal. For the perturbation effects diagnosis, we provide a detailed visualization to explain how the perturbation causes impact in both overview and detailed aspects. And finally, we want to make the sensitivity index list more flexible for users to explore the perturbation space under certain constraints defined by domain experts. Now let's dive into the detail. To identify the instance level sensitivity, as we mentioned earlier, we calculate the overall sensitivity index. And when we also specified into positive and negative sensitivity index in terms of the categories, which denotes how certain groups of nodes are influenced through the perturbation. Therefore, we use the L1 norm as distance metric so that all the measures are constant. We integrate all the measures into sensitivity index list to facilitate users to look for potential targets for perturbation effect diagnosis. Once the instance is selected, the user will be able to perform the detailed perturbation effects analysis for that instance. So generally, we employ both overview and detailed inspection to help users understand the ranking change influence in a variety of dimensions, which includes statistical information, ranking distribution, and topological influence. For statistical information integration, we designed a radar chart to show the overview of influence caused by the perturbation, which includes the number of influence nodes, the number of influence nodes who have ranking increased, and the degree of the node, etc. The reason for choosing the radar chart is that the polygon glyph can quickly give users an impression of the effects of the perturbation. We also place a positive and negative influence on the left and right side separately, which is suitable for comparing differences. Those dimensions can also be easily extended in case some more statistical information is needed. To review the ranking changes in terms of distribution, we designed radar ranking change distribution view, which is basically a bar chart with axes showing original ranking position and y-axis for ranking changes for each node. We scale both axes so that if we rotate the bar by 90 degrees, so that we can infer the ranking positions of the node after the perturbation. The color is encoded as categories of the node. One special feature of the ranking task, as some related work mentions, is that in terms of the items that are not top K ranked are less important than those in the top K. Thus, we designed top K distribution view only consider how top K proportion of different groups change before and after the perturbation. We employ two donor charts for original and the perturbed top K proportion respectively, and the K can also be manually set, and the view will be dynamically rendered when the K is given. So finally, we designed the influence graph view to show the relationship between influence and topological structure. The general idea is that we build an equal network with a removed node as the center of the network, and then we connect all the influence nodes based on the topological structure. We denote the hop1 node, which is the neighbor of the removed node as its successors, and hop2 node, which is a neighbor of a hop1 node as its successors, so on and so forth. For those nodes who do not have any connections with the removed node, we mark them as hop-inf node, linked with dash line. We ended up building a tree structure to show the different influence distance between removed node and the influence node. The reflected intuition is that from hop1 to hop-inf means that the direct to indirect influence. We employ the radial layout so that the nodes of the same hop level are clustered, which is easy for users to obtain pattern. The last functionality of our framework is constraint filtering. Suppose now we have the calculated sensitivity index list, and here's the current ranking results. We know that the first node has the highest sensitivity index, but in real-world application, this perturbation is not likely to happen. For example, if we remove it, the ranking positions could be heavily influenced, and the top K content could be disproportional in terms of certain categories. Such perturbation is easy to be discovered, let alone we remove the most relevant one. Instead, the users may be interested in this. What if we protect most of the top 10 content from ranking jobs, and then we see what else has the largest influence? So now we know from a filtered sensitivity index list that the node D is what we look for. And the perturbed influence is relatively large but subtle. The system allows multiple constraints to be applied to the sensitivity index list, and the constraint view is also suitable for extension based on the needs of domain experts. Now we demonstrate our case study to explore the sensitivity of HITS on political block citation network. We consider the dataset as political forums where members post views and opinions on certain political topics. The search results ranks are determined by the graph ranking algorithms, and higher ranked opinions are more likely to be read and shared. However, there is a possibility that the nation-state actors can manipulate the ranking results so that certain political opinions are more likely to be exposed to the public. As such, block managers and social scientists may wish to collaborate with ranking algorithm developers to make sure such ranking results are fair and stable with respect to potential perturbations. We also made some assumptions that any ranking changes of top 5 blocks is riskier as it is easy to be discovered. Thus, we will add a constraint of that top 5 nodes should not be influenced to have ranking drops in this task. Okay, so here's the demo. As you can see that the left panel is the sensitivity index list for all these instances. On the bottom, there is a constraint filtering section. Given assumptions as we mentioned before, we apply constraints that exclude all the perturbations that would cause the ranking of top 5 nodes to decrease. After rule is applied, the table is refreshed. We find the liberal block, so liberalauthors.com appears on the second row, which satisfies our requirements. By exploring why this blog is so influential, we find that most of the ranking changes happen in the range between 50 and 150, since only mid-tier ranks are impacted. The effects of removing this node is subtle, meaning that this change is not easily observable. However, the impact is significant. We can also see the top 100 results that the proportion of liberal block results has decreased by 5%, thus subtly shifting the size content. The influence graph view shows that the removed node has a direct influence on the majority of liberal nodes, and as the influence distance increases, more conservative nodes are indirectly influenced. To the conclusions, in this work, we have proposed a visual analytics framework for auditing the sensitivity of graphics ranking methods. We have also provided a novel representation of to illustrate the relationship between ranking influence and topological structures. The major limitation would be handling the visual elements when the data gets larger, and we also think about supporting many other perturbation methods into our framework. So that's been our work. Thank you for your listening, and now I'm happy to answer some questions.